In this video, we work problem 4A from the written homework number 1 in the spring 2021 semester for differential equations. We're asked to find the largest subset, R, of the xy plane, for which the initial value problem consisting of this differential equation and this initial condition y of x naught equals y naught is guaranteed to have a unique solution. And so they give us this differential equation, and we pair it with this initial condition to get an initial value problem. In order to find this subset R of the xy plane, for which this IVP will have a unique solution for any x naught, y naught in the region R, we need to do two things. We need to identify the function f of xy. That's this function. So remember, our theorem looks like this, or the IVP in our theorem looks like this. So we need dy dx, or the derivative of some variable with respect to another variable by itself. And on the other side, that's the function of both the independent variable and the dependent variable. And remember what our theorem said. Our theorem said that if this function, f, and its partial derivative with respect to y are both continuous on a region that contains this point, x naught, y naught, then the IVP is guaranteed to have a unique solution. So I'm going to state my version of the theorem in my own words. It says if, given this IVP, if f and the partial of f with respect to y are continuous on an open region R containing x naught, y naught, then the IVP has a unique solution. Now, it's wordier in the original version, but that's the basic idea. So we just need to figure out where this function f of x and y and its partial derivative with respect to y are continuous. The place where those two regions in the xy plane overlap, that is the open region R, because I need this one to be continuous and this one to be continuous at the same time. So we just need to think about the continuity of this function f. Now, when you're dealing with a function that is given by just a single formula like this, in terms of known functions that we've studied from pre-calculus, we've got a logarithmic function. It has a polynomial inside. We've got a polynomial in the denominator. Oops, it's a minus. There are basically three issues that we have to worry about. This function will be continuous on its domain, and its domain will consist of all points xy in the xy plane that do not cause three problems. So let's say this, f is continuous on its domain. Just because of the nature of the function that we have here, I can look at this and tell that it's going to be continuous on its domain because it's made up of those functions that we're familiar with, functions that we've studied in pre-calculus, including compositions of those functions and, of course, quotients of those functions. And we're going to say that the domain of f is a set of all xy pairs that satisfy certain requirements, and those requirements are going to go over here. So this function will be continuous here, but if I'm trying to find this domain, we just need to think about which xy values won't work. We're going to exclude the xy pairs that cause the following. Division by 0. We all know that we can't divide anything by 0. Negative, or, whoops, even roots of negative numbers. Can't take an even root of a negative number because then we would get a complex number, and we're interested in real valued functions here. These are real valued functions of real variables. And then the third thing that we cannot have is a logarithm. Logs of negative numbers or 0. We can't take the log of a negative number in the real number system, and we can never take the logarithm of 0. So those are the things that we're looking for. We look over here and we're looking for anything that could cause division by 0. Well, we'd have a problem when this denominator is 0. And we'll have a problem when what's inside here is negative or 0. So the expression inside the logarithm has to be positive. So the domain of f is the same region where that function f is continuous, is the set of all xy pairs such that this denominator is non-zero. So we don't want to divide by 0. And the expression inside the logarithm is not negative, it's not 0, so that would mean it has to be positive. So that's our domain. Now, we were not asked to sketch the subset R of the xy plane, but I would recommend that you sketch it. For most of the quizzes, I have students sketch it. In most of my examples, I have the students sketch the region as well. So basically, we need to sketch this now, and then we need to compute the partial of f with respect to y and sketch its domain and then see where they overlap. Now, with this first inequality, or actually the second inequality, since it involves a y to the first, I would recommend that you isolate y by adding x cubed to both sides and then subtracting 2 from both sides. And then you see an inequality that has to be satisfied. That makes it a little bit easier to graph. So we want all the xy pairs for which y is greater than, strictly greater than, x cubed minus 2. Now x cubed minus 2 looks like the x cubed graph. It's just shifted down 2 units. When x is equal to 0, y would be equal to 0 if we were on the y equals x cubed minus 2 graph. I'm sorry, I just misspoke. When x is equal to 0, y would be equal to negative 2 if we were on the graph where there's an equals sign here. If x is equal to 1, we would have a 1 minus 2 is negative 1. If x is equal to negative 1, we're going to get a negative 3. And that's just how that works. At x equals 2, we're going to have 2 cubed minus 2, which is 8 minus 2, which is 6. And there's going to be some symmetry. We should see a point just like that over here. Not to scale, but you get the idea. At negative 2, should have a point, something like that. And if this were a greater than or equal to sign, I would draw a solid curve. But since it's a strictly greater than, y equals x cubed minus 2 is the boundary. So we don't want to include any points on this curve. So we'll use a dotted line here. And then we're looking for the points where y is greater than that. And I believe y is greater than that on this side. But just to check, you can always test a point, plug in any point that's not on the boundary curve and substitute into the inequality and then see if that point satisfies the inequality. So let's test xy equals 0, 0 in this inequality. If y is 0 and x is 0, oops, we get this. And that simplifies to this. And then you just look at it and you ask yourself if that's a true statement or not. Since 0 is greater than -2, that's true. So that means we're going to shade the region containing 0, 0. So I would shade over here, but I want to do the rest of this first before I do that. Now, if you're wondering why that works, most of the time we talk about this in pre-calculus. Basically, this y equals x cubed minus 2 splits the plane into 3 parts, where y is equal to x cubed minus 2 on this curve. Y is going to be greater than x cubed minus 2 on one side and less than x cubed minus 2 on the other side. It's splitting that region into all 3 parts. You just have to figure out which part is the one where y is greater than x cubed minus 2. To decide whether y is greater than x cubed minus 2 is on this side or this side, you just plug in a point on one of the sides. So we plugged in 0, 0. If 0, 0 satisfies that inequality, then it turns out that all of the other points on this side will satisfy that inequality as well, because of the fact that y equals x cubed minus 2 separates the plane into these 2 parts. So if you get a true statement, you shade the side containing your test point. If it was a false statement, you would know that that's not true, so it would have to be the other side. So we're eventually going to shade over here, but we're not finished yet. So we know that the domain is the set of all xy pairs such that y is greater than x cubed minus 2, and this inequality must be satisfied as well. X squared minus 2xy minus 15y squared can't be 0. So what I would recommend you do is factor that, and we want to graph that set as well. First times first will be x squared, so we'll have an x and an x here. And notice that this middle term has a y in it, and this last term has a y squared. What that means is that when I factor this polynomial that involves 2 variables, I can just ignore the y, at least initially, and focus on factoring something that looks like this. So I ask myself, first times first must be x squared, so that must be x and x. And then I ask myself, what 2 numbers multiply to give me a negative 15 and have a sum of negative 2? Well, 5 and 3 will give me 15. If the 5 is negative, negative 5 times 3 will give me negative 15. Negative 5 plus 3 would give me negative 2. So if I were just factoring this, I'd have a minus 5 here and a plus 3 here. But we're not factoring that. We're factoring this. So this factors very similarly to the way this other one factored. In order to make this a negative 15y squared, we'll put a y here and a y here. So that negative 5y times 3y gives us the negative 15y squared. And outer times outer isn't just 3x, it's 3xy now. And inner times inner is negative 5xy. 3xy minus 5xy gives us that negative 2xy in the middle. So we just factor that by treating it the way we would treat a traditional trinomial, and then sort of tacking on that y, because when we do the outer times outer, inner times inner, if we multiplied by y here, that will add a y here. And if we have 2 y's, the end, this times this will give us a constant times y squared. Okay, so this factors this way. And we're saying that y has to be greater than this, so we're shading over here, and this times this cannot be 0. The only way that this product is non-zero is if this is not 0 and this is not 0. So what I would recommend you do is take each of those factors and set them equal to or not equal to 0 and then solve for y. So we're still talking about the domain of f, which is the same as the region where f is continuous. So this is the set of all xy pairs such that y is greater than x cubed minus 2, and x minus 5y is not equal to 0, and x plus 3y is not equal to 0. Because the only way a product is non-zero is if both factors are non-zero at the same time. And if I take that inequality and I solve it for y, by subtracting x from both sides and then dividing by -5, I get y equals 1/5 x, or y is not equal to 1/5 x. And over here, if I solve this one for y, I get y is not equal to 1/3 x cubed. So the points x, y cannot lie on this line or on this line. So I'll just graph those two lines, y equals 1/5 x. So there's 5, we go up 1 and over 5. Not to scale, but you get the idea. And then the other one is y equals -1/3 x. So we go down 1 and over 3. Okay, so the question becomes, well, where is f continuous? It's continuous on this set, which is the same as this region over here. It's this part, and that little triangular piece, and this part, and this piece over here. Because we want y to be greater than x cubed minus 2, which means we're on this side of that curve, and x and y cannot lie on that line or that line. Okay, so we need f to be continuous, and it's continuous on its domain. We just found its domain. We also need the partial of f with respect to y to be continuous on the region R that we're interested in. So we need to find that partial of f with respect to y. And then figure out where it's continuous. So we have the log of y minus x cubed plus 2 in the numerator over x squared minus 5xy, or minus 2xy, minus 15y squared in the denominator. I would just use the quotient rule for this. We're going to get the bottom function times the derivative of the top function. Now, that's a composite function. We've got a polynomial inside a logarithmic function. So I need to use the chain rule. The derivative of log of some function is 1 over that function. Oops. There we go. Times the derivative of the inside with respect to y, treating x as a constant. Well, the derivative of y with respect to y is 1, and of course the derivatives of all these pieces are 0. So this is the bottom function times the derivative of the top function minus the top function keep wanting to put an exponent on that y for some reason, times the derivative of the bottom function with respect to y, treating x as a constant. And of course, all of that logarithm is multiplying this over here. Well, the derivative of x squared with respect to y is 0. The derivative of this constant times y with respect to y is just the -2x. And the derivative of -15y squared is just -30y to the first by the power rule. And we're going to divide all of that by the bottom function squared. Now you could simplify that if you want to, but simplifying it actually isn't going to help us find the region where that is continuous. We can just look at this and tell where this is continuous. This f is made of functions that we're familiar with, so it's going to be continuous on its domain. The partial of f with respect to y, I mean. And its domain consists of all xy pairs such that we're not dividing by 0, and we're not taking logarithms of negative numbers or 0, and we're not taking even roots of negative numbers. But this denominator is the same as the original denominator. This can't be 0, but we already knew that that couldn't be 0 because of the domain of f, not the domain of the partial of f with respect to y. And we know that this can't be 0, but it was inside the logarithm anyway, so it wasn't allowed to be 0 last time. And then, of course, this has to be positive because we can't take the logarithm of a negative number or 0. And we already knew that from last time as well. So we have y minus x cubed plus 2 must be greater than 0. So it turns out that in this case, the restrictions on the partial of f with respect to y are exactly the same as the restrictions on the domain of f. The restrictions on this domain are the same as the restrictions on the other domain. I may have misspoke for just a moment there. So this happens to be equal to this. Both functions are continuous on their domain. Since both of those are continuous on their domain, the largest subset are of the xy plane. Where the IVP is guaranteed to have a unique solution. Is this set. And we simplified that earlier. It's a set of all xy such that y is strictly greater than x cubed minus 2, and y is not equal to 1/5 x, and y is not equal to negative 1/3 x. And then if we were asked to graph that, and we're generally asked to graph that, I would be prepared to graph that on your quiz in this class. We're going to graph something that looks like this. Now, in practice, if I have an inequality and I'm trying to decide how to graph it, if I'm setting it not equal to 0, usually I just have to factor that and then graph each of those pieces separately. And if I have an inequality like this, I usually try to get y by itself. Another common form that you'll see is the forms associated with circles or ellipses. I know this is unrelated to this question, but it is related to your quiz. If, let's say, you had to graph something like x squared plus y squared is strictly greater than 4, well, the boundary there would be x squared plus y squared equals 4, which is a circle of radius 2 centered at the origin. And it turns out that when we're inside that circle, let's say at 0, 0, this inequality is false. X squared plus y squared, if we're at 0, 0, is just 0. 0 is not greater than 4. If we're outside that circle, x squared plus y squared is greater than 4. So that's what that set would look like. So as you're thinking about how to prepare for a quiz over this, just remember some functions from pre-calculus and how to graph the solution sets of inequalities, and of course factoring. And if something says not equal to, you use a shaded or a dotted line. If it's equal to, you would use a solid line.